Okay, so here's where we were last time. We were talking about Jordan canonical form. It's a complicated structure, but it has some nice features. Quick reminder, nice things about Jordan canonical form. It's always achievable by way of change of basis, conjugation, whatever you want to call it. Right? Similarity. It's also almost diagonal, so it's a great consolation prize. If you were trying to diagonalize, we like diagonalizability because having just numbers only along the diagonals, nice. It's gives us a lot of zeros to work with. Some other advantages that we haven't seen yet. Being almost diagonal seems like it would be almost as good as being diagonal. Right, and that ends up being kind of true. So anyway, certainly it's a good thing, and there's a lot to say about it. I cannot. Well, whoops, I'm in the wrong mode. We cannot conveniently prove these things that I've just stated. That you can always put a matrix into Jordan canonical form. That's the hard proof. Can't reasonably do it. We cannot prove reasonably that it's unique up to rearrangements. That's also hard to prove. How do you find a Jordan basis? It's tough in general. There are some cases where the way I give you some arithmetic will allow you to sort of automatically infer a Jordan basis, and we'll talk about that later. But in general, here's a matrix A, find a Jordan basis. It's hard. Okay, so we're not going to do that either. So there are certain situations where Jordan form, Jordan bases kind of work out nicely. For one thing, I'll observe that if the matrix is diagonalizable, if you think about it, diagonal form, having the matrix have a diagonal form, you can think of each diagonal entry as a little itty-bitty little 1-by-1 basic Jordan block. So in fact, every matrix that is diagonalizable is Jordanizable. The diagonal form is the Jordan form. So, that's, sort of a trivial special case. And of course, the basis, the Jordan basis is just made up of the eigenvectors, as the eigenvectors were how you diagonalized. Okay. Here's another little, low dimensional example. Kind of a lucky break type situation. This kind of thing is, useful. Recall, given a matrix, we know how to write down characteristic polynomials. Let's suppose that we had a characteristic polynomial that looks like this. Here's some free facts that we get to infer. This factor, come on, stylus. This factor tells us an eigenvalue and a multiplicity. Now, we already know some things about Jordan form and how Jordan form relates to eigenvalues and multiplicity. So we know that there is a 2-by-2 eigenvalue block with eigenvalue 1. And the beautiful thing about it is there are only 2 of those possible. 2 is just a small number. There's only so many ways to satisfy the rules of Jordan form with those constraints. So that one factor in the characteristic polynomial, we already almost, except for a single choice, we almost know that part of the Jordan form. And if you look at the other factor, this factor here, multiplicity 1, eigenvalue 3, well, that means there's a 1-by-1 eigenvalue block. And of course, there is only one possible eigenvalue block of that sort. So, simply looking at the characteristic polynomial, we'll almost have figured out the Jordan form already. Okay. The last little bit comes to eigenvectors. If you look at this first eigenvalue, here, there are 2 possibilities about the eigenvectors. One possibility is that there's 2 eigenvectors. If there are 2 eigenvectors, then there must be 2 basic Jordan blocks. 2 basic Jordan blocks would look like this. Namely, that's my Jordan form. Right? Whereas the other case, it's also possible, maybe you have only one eigenvector. That would suggest you have only one basic Jordan block, namely that is your Jordan form. So you can you can figure out what the Jordan canonical form looks like just by sort of process of elimination based on the low-dimensional, the conveniences of the low-dimensional situation you're looking at. Okay. All right. last observation, and it's just another sort of a quickie observation about what Jordan form looks like. Let's think about this characteristic polynomial here, and let's focus one at a time on factors. Let's look at this factor here. We know we have an eigenvalue block that's 4 by 4. A 4 by 4 eigenvalue block. What's going to be inside of that? Lots of possibilities. One possibility is that you have a 4 by 4 basic Jordan block. Let me just circle that for a moment. I'll come back to the connection momentarily. What's another possibility? Another possibility is that you have a 3 by 3 eigenvalue block and a 1 by 1 eigenvalue block. All right, so I'm going to circle that right there. Now, what's going on? What's the connection between these? The connection between this little arithmetic and the pictures that I'm drawing over here are, think about the diagonal entries. How many diagonal entries are inside of which of each of the basic Jordan blocks? With the purple picture I'm drawing, all 4 of the diagonal entries are inside of the first and only basic Jordan block. 4. Okay. In the second picture I've drawn here, there are 3 diagonal entries inside of the first basic Jordan block. There's 1 diagonal entry inside of the last Jordan block, and so there's 3 in one and 1 in the other. In both cases, we're talking about there's a total of 4 diagonal entries. Those 4 diagonal entries are going to sit inside of, these disjoint basic Jordan blocks. And so roughly speaking, how you draw the basic Jordan blocks is just a question of how are you going to partition those 4 diagonal entries into different blocks. Said differently, how many different ways can you view 4 as being a sum of positive integers? Continuing along real quick, 2 plus 2 would correspond to a 2 by 2 eigenvalue block, and then a basic Jordan block, and then another 2 by 2 basic Jordan block. It would look like that. So if you want to know how many different structures, how many different basic Jordan block structures are there inside of the evident 4 by 4 eigenvalue block, you're just going to write down arithmetic like this. How many different ways can you make numbers add up to 4? Positive integers add up to 4. And there's only so many different ways to do it. So one at a time, you can look at the factors, enumerate with this arithmetic all the different ways to write the basic Jordan block structures, and count, keep track, and you can deduce all the possible Jordan canonical forms. Okay. All right. We're going to do some neat things with Jordan canonical form later on. Quick reminder. Our big application of diagonalizability in Jordan form, big application is going to be differential equations. We're going to find some really important differential equations to solve in Chapter 6. When we get to Chapter 6, diagonalizability is going to be one of the big tools. And what to do in the non-diagonalizable case, capitalizing on the fact that we know it's in Jordan form, we're going to find some methods that will allow us to still solve those differential equations using what we know about Jordan form. Okay, so that's going to be later on. All right, moving along. We're going to skip Chapter 6 for the moment. We're going to jump up to Chapter 9 out of numerical order. It's a judgment call. It's kind of a, choice anyway. So it's a quick word about why I'm going to do that. It's not that it really matters. The book obviously does Chapter 6 before Chapter 9, right? So there's nothing wrong with that. I'm going to do Chapter 9 before Chapter 6, just like my predecessors did, because Chapter 9 is about linear algebra, right? Chapter 5 is about linear algebra. And linear algebra tools are nice to have in our toolbox when we go on to apply those tools to applications. So I'm thinking of Chapter 6 as our big application. Wouldn't it be nice to have all of our tools prepared at our disposal, and then we can use those tools more conveniently when we're doing the application of Chapter 6. So anyway, like I say, it's just a choice. It doesn't really matter, but that's what we're doing. Going on into Chapter 9, we're going to define something called an inner product space. So I want to say a few words before I get to the details about inner product spaces. about abstractions. So recall I gave y'all a whole speech, long speech about abstractions back in chapter 2. We were talking about vector spaces. Okay? So reminder, here's what happened. Chapter 2. We were dealing with Rn, vectors in Rn. We observed that you can add vectors in Rn to get other vectors. You can multiply vectors in Rn by scalars to get other vectors. Therefore, you can do linear combinations of vectors in Rn to get other vectors. So we have this construction of linear combinations. Right. Okay, so then we also noticed you can talk about linear combinations of functions. Same algebra, different objects. Okay. Then we observed that you can do linear combinations of matrices, and you can do linear combinations of various other, kinds of things. All different as objects, but with identical algebraic structures, obeying identical algebraic rules. Then I made the silly observation of a theorem. I wrote down a theorem about linear combinations of vectors in Rn. Stated the theorem that linear combinations of linear combinations give you linear combinations. Stated that as a theorem in Rn. Proved it as a theorem in Rn. And then asked, what if we were dealing with functions? And I had to confess that, my previous theorem doesn't apply. My previous theorem was about vectors in Rn specifically. Okay, so we restated the theorem about functions. We reproved the theorem about functions. We noticed that the proofs were practically identical. I mean, they were sort of hair-pullingly, come on, it's the same thing, right? Nevertheless, we had to write it down again. And then, now we have a theorem that applies in Rn. We have a theorem that applies to functions. What if I'm taking linear combinations of matrices? Right? So we would have to state the theorem all over again, prove the theorem all over again, because the objects were changing. Okay, so we notice the preposterousness of this strategy, how silly. The point to take about that theorem that we kept proving over and over and over again was that it was a theorem about the algebraic structure. It wasn't a theorem fundamentally about the objects themselves. The objects being long pointy things in Rn. That wasn't what matters, right? It didn't hinge on the nature of functions themselves. It didn't hinge on what matrices really look like. All that the theorem was really talking about is the algebraic structures. If you can add things, if you can multiply by scalars, if the algebra of addition and scalar multiplication obeys certain key properties, if the algebra goes the way algebra kind of sort of ought to go in the sense of 8 properties that we could write down. Anything satisfying those rules in the abstract, completely abstract rules, no commentary at all on the objects. Anything whose operations satisfy those rules, we can state and prove a theorem about those things, independent of what kind of objects they are. So we create this abstraction of a vector space as a self-defense tool. I don't want to have to keep stating and proving morally the same theorem over and over again. I want to just say, look, I'm going to define an abstract thing. Anything that algebraically behaves a certain way, I don't care what the objects are. I don't care. We don't want to have to worry about what the objects are. Just anything that algebraically behaves a certain way, let's give it a name. Let's call it vector space. Let's state and prove the theorem about vector spaces. Do it the one time. Right? And then, any vector space that we've previously encountered, even better, any vector space that we ever encounter in the future, we already have a theorem, we've already proved it. You only have to do it the once, right? So it's a very powerful idea. Again, a common misconception that I like to clarify at a time like this is a lot of times students think of abstraction as the opposite of application. This is wildly wrong. Abstraction is what makes an idea apply as broadly as possible, right? When you state and prove a theorem about vector spaces, It is literally the abstractness. It is literally the fact that you didn't say what those objects were that allows that theorem to apply broadly to all possible vector spaces independent of what the objects are. So it's a powerful observation. Abstraction is breadth of application. All right. Okay, so here we are. I'm going to create a new abstraction. We have a slightly different context here. I still want to talk about modeling things on Rn. Rn was our model when we were talking about vector spaces. We were thinking about how stuff works in Rn. You can add vectors in Rn. You can multiply vectors in Rn by scalars. And those algebraic constructions, addition and scalar multiplication, that's what I was dealing with back in chapter 2. And so, we talked about those operations and the algebra features that they satisfy. Defined our abstraction, all modeled on those features of Rn as and this is our template. This is what we were thinking about. Okay. Conspicuously absent from that consideration was the dot product. Right? The dot product's in Rn. How come we wouldn't talk about the dot product structure of Rn? Yeah, we didn't need it at that time. So I'm going to make a new abstraction. The idea is to say, look, I want to think about things that behave like Rn. We had huge success thinking about things that behave kind of like Rn in defining vector spaces. We did powerful things with vector spaces. We solved differential equations with vector spaces and the ensuing resulting ideas of dimension and independence and span and bases and all that kind of stuff. Solve differential equations. So here's another point of view of Rn. I can think of all the vector space properties, addition, scalar multiplication. And now let's add in addition, the dot product. Let's try to write down, roughly in some sense that we're happy with, what are these three operations? What are the defining characteristics of how these algebraic observations behave? Not what the objects are. Forget about the objects, right? We don't want to tie ourselves down to details. We just want to talk about how do these operations behave, declare that anything that behaves like them to be one of our new abstractions, and then start playing with it. Okay. So in order to do that, I have to remind you about the dot product. Don't forget the dot product in Rn is this formula right here. Flashbacks to Math 212. Here are some facts about the dot product. 4 important facts about the dot product. Make sure you remember all this stuff. If you're a little rusty on Math 212 about dot products, it'd be a good time to brush up. Yeah, okay. Real quick, let me mention there is something importantly different between what I've written down in this fourth property and how the book writes their fourth property. I'm observing here that a self-dot product is never negative, and furthermore, that you get 0 only in the case of the 0 vector. The book does not include this non-negativity. That ends up being a problem a little bit later on. I'll try to remember to mention exactly where the problem comes up when we get to it. But anyway, that is a little distinction. I'm writing this down in a way that I think is going to allow us to do more things. That's a nice advantage. Okay, so 4 facts about the dot product. Here are 3 more facts about the dot product. Bringing up the question, what's the difference between a fact and a more fact? And I'll reveal that in a couple of minutes. For the moment, let me just say, also true. Also, remember these observations from Math 212. And then still more facts. More true observations. Excuse me, about dot products. Flashbacks to Math 212. Make sure you remember all these. And again, why am I noting these as different? Explanation to come later. Okay, so what I'm going to do is use these first 4 as the defining characteristics These are the features of the dot product that I want to model. Say, look, anything, when I say something behaves like the dot product, what I mean is something that behaves like the dot product in the sense of these 4 properties. Anything that behaves like this, I'm going to say is what we call an inner product. Inner product just means it's kind of like the dot product in these senses. And here's where we write that down. On the next page. So a function satisfying these 4 properties, note that these are just rewrites of those 4 properties on the previous page. Any such thing is called an inner product. And if you have a vector space, now that's a mouthful, right? A vector space, oh wow, so we have to have an addition operation, we have to have a scalar multiplication operation, which have to satisfy 8 properties, right, that we've enumerated. If you have a vector space and an inner product all together, that's called an inner product space. So an inner product space is it's a souped up vector space. It's a vector space with an additional structure, that being an inner product, that being kind of like a dot product. Okay? How we doing? Everybody on board? Why we care? Not yet clear. All righty. So some examples. My first example is a silly example. I claim that Rn, the vector space of Rn. Okay, let me color code like I did before. The vector space of Rn. So now there's a lot that comes along with that. That means the usual vector addition in Rn, the usual scalar vector multiplication in Rn, combined with this as my formula for my inner product. These things together form an inner product space. In order to check this, well, we already know that Rn is a vector space. That's a freebie. All we have to check is that this inner product, defined by the dot product, satisfies our 4 requirements. I claim this also as a freebie because, of course, the dot product was our model. We wrote down those 4 properties because the dot product satisfies them. So, of course, the dot product satisfies them. Okay, so, like I say, it's a silly observation. Good general rule of thumb, your model for an abstraction always satisfies the rules for that abstraction. Okay. All right, now here's a non-silly example. Here's a very non-trivial and very important example. We're going to take as our vector space C. I hope you all remember C. This is a collection of all continuous, real-valued functions defined between A and B. That's a vector space. See Chapter 2. This is a vector space because you can add elements of that set. You can multiply by scalars elements of that set. And all the usual rules apply. All right, so here is an additional bit of structure that I'm going to define. This is our new operation that I claim behaves kind of like a dot product. This is a weird little formula. Let me walk you through what this formula says. If you give me 2 vectors, keep in mind F and G are elements of the underlying vector space. So these are vectors. What I'm going to call the inner product of those 2 vectors is what you get by plugging into this great big formula. We're going to take the 2 vectors, multiply their output values, their real valued output values, and then do an integral from A to B of that product. Claim that this is an inner product. This is an inner product on C, and therefore C combined with that inner product is an inner product space. Shoot, I should have written that down somewhere. Anyway, here, let me steal from the previous example. That is an inner product space. Now, this is a non-trivial example. It's not immediate that this is true. This really has to be checked. So let's see, I need to zoom out a bit. You've got to check. Of course, we know C is a vector space. That's not an issue. You've got to check all 4 of these properties. And this is something that everyone should do at least once. So please take that as an exercise, for practice. Good news. The first 3 of those properties are really easy to check. And it's just a matter of, interpreting them appropriately given this new function, this new operation. And using, roughly speaking, Calc 2, existing properties of Calc 2 to confirm that, yes, indeed, those just work exactly like they should. So the first 3 are pretty straightforward. This 4th one is not. This 4th one is tricky. Specifically this part of it. Observing that you get equality only in the case of the 0 vector. The 0 vector being the vector in C, the function that is exclusively always valued at 0. So to show that is the only vector whose self dot product can be 0 is requires some careful thought. Calc 2 does not directly handle that by itself. These are not just sort of like, plug into old Calc 2 properties. You've got to use continuity. The continuity of these functions is key. So this is a tricky argument. You got to think it through carefully. I encourage everybody to give that a try. If you don't see how the continuity is essential as you go through and try to make that argument, come talk to me or come talk to the TAs or ask in discussion section. It would be a fine question to ask about in discussion section. Definitely some subtle points to be made there. But you got to use the continuity. Okay, something to think about. Okay. Let me say a few more words about this specific inner product. This formula right here is an inner product. This is called the L2 inner product, so it is. It's got a name. We tend to name things that come up a lot, things that are important. This one certainly is. This specific inner product has tremendously powerful applications, and exactly why that is it's a long story. We won't be able to actually get to. The details of all those applications. But I just want you to know what is at the end of the road. What can you do with this construction eventually? And 2 things that I'll point out. One of them is Fourier series. So those of you who took Calc 2 here at Duke have already seen Fourier series. If you have not taken Calc 2 at Duke, in Math 353, you will see Fourier series. And Fourier series are, when you see them in a Calc 2 class, looks like it's calculus. It looks like an analysis kind of thing. It's integrals and functions and stuff like that. It just feels like a very calculus collection of facts. A much better way to think about Fourier series is from the point of view of linear algebra, and specifically thinking of Fourier series as a statement about linear algebra done in this inner product space. So this specific inner product, very powerful tool, because this inner product behaves, like per our model, kind of like a dot product. Think about all the things you could do with dot products back in Math 212. Doing that kind of thing allows you to come up with and motivate and prove Fourier series. That's kind of neat. Here's another one. And this one is harder to talk about, but it's, I think, still a pretty interesting punchline: image compression. Right, so there's some neato things that you can do with fancy algorithms and computers to take a tremendous amount of data that it takes to store an image, and instead, kind of store approximately something that's almost indistinguishably, just practically identically the same image, but with much, much, much less data. That's a neat trick, right? How do you do that? Right? Well, it turns out if you view the vector space of images And if you use a construction morally identical to this to create then an inner product space structure on the vector space of images, right? And make some other additional, very clever, very powerful choices. An argument kind of analogous, morally kind of analogous to the argument that leads to Fourier series, but in that other context of two-dimensional images with an analogous inner product. That's one of the big ideas of image compression is finding ways to capitalize on how this formula behaves kind of like a dot product. Okay. Again, the details of that are more than we can reasonably do in this class, but I wanted you to know what's, where does this eventually lead, and why is this useful? And it's just, it's too bad that we can't actually fill in those details right now. Okay. All right. Here's another one. This is just to have another example. Let's start with this formula right here. Now, that's just the dot product. If you've got a vector v and a vector w, how do you take the dot product? Well, you multiply and add the corresponding coordinates. Wait a minute, coordinates with respect to what basis? Well, the coordinates of the vector, by which we mean what we typically talk about as, the coordinates of the vector, that means coordinates with respect to the standard basis. So, this is just this is what you might call a fussy way of writing down the good old standard plain old dot product. Okay. Well, that said, you could instead take a couple of vectors in Rn, look at their coordinates with respect to a different basis that gives you a different list of numbers for each vector, and you can then multiply and add those coordinates, those very different coordinates, and you get a very different construction. It is not the same as the what you might call the standard dot product on Rn. Looking at dot products with respect to a different basis, very different formula. Not the same, but it is still an inner product. And that's a nice little exercise. You can directly confirm that this new formula, dot product with respect to a different basis, satisfies all four of these formulas. Okay. Quick FYI, exercise 9 in this section. So one of the assigned exercises for the homework. It does not at a glance look to be about this inner product, but the inner product in exercise 9 is equivalent to this inner product. So I encourage you to think about that. As you're going through and doing exercise 9, try to make the connection. Why is exercise 9 in fact equivalent to this inner product right here? And that's a good point of view to think about. Okay. All right, so we've seen some examples. We've got our vector space, we've got our inner product space construction. Roughly, again speaking, the new tools, the new objects are the inner product that has to satisfy these four properties. Remember, those four properties came from these four facts about the dot product. Okay, now here's a natural question to ask. These facts are also true about the dot product. I want inner products to behave like the dot product. The dot product satisfies these rules. Why wouldn't I want inner products to satisfy these rules also? Right, I want inner products to behave like dot products in this sense. Don't I also want the inner product to behave like the dot product in these senses? Shouldn't these be included in the definition? It seems like they certainly should be. Right? Okay. Here's why I didn't put them in there. This is very nice fact. But it's not that we don't want those properties. It's that they're free. They are absolutely free. Any operation that satisfies these four orange properties automatically, without requirement, automatically satisfies these three properties. And let me give you an example of what I'm talking about. Let's look at property, oh gosh, I've already forgotten my colors. Yeah, so these two properties right here. Let's suppose that I've checked these first two properties. Well, if you can commute, and if your inner product has what you might call a right distributivity, it immediately follows that it must have a left distributivity. So think about how silly would it be to require that I go through and check this and go through and check this, at which point I already know this has to be true. How silly would it be to force me to go through and manually check it anyway? I already know it's true. Those properties immediately give me this property. You don't need to check it again. Okay, so I separate these as different properties. These make up the definition of the inner product. These are not required because these are free. They are automatic. It's not that I don't want them, it's that I already get them. That's the point. Okay, everybody on board? It's a good little game to play. Think through how would you prove these others from those. Okay, now there are a couple others I want to talk about here. I want to talk about something called bilinearity. These two properties are what it means to say that an inner product is bilinear. Do y'all remember multilinear from back in chapter 1? It's basically saying that, one vector at a time, the operation is linear. Bilinear, same thing, just when you have two vector inputs. So here, for example, let me show you what I mean by linear in the first entry. Let's look at this construction, this operation. Let's look at this as a function on the first entry. Let's fix W, in other words. With W fixed, we have a function here on the left entry. And notice what we have. This property here says that if you put a linear combination in, then you get a linear combination out. Linear combination on the inside, linear combination on the outside. It's just saying linearity of the inner product thought of as a function of the left entry alone with the right vector fixed. Okay. So linear in the left entry, and then analogously, the second line here says linear in the right entry. This is what I mean by linear in the right entry. Okay. Also automatically follows from the definition. All right. Back up to our initial list. We have first set of facts that were our definition. We have the second set of facts that we don't have to include as part of the definition. They're freebies. They come along automatically. I don't have to do them. What about this third set of properties down here? Are these automatic? No, they aren't. That's disappointing. So these are not free. So is it that I don't want these to be true? Should these be part of the definition? Why didn't I include these as part of the definition? And I claim I can't. I cannot require these to be part of the definition because if you look at what these properties are saying, these properties down here are not exclusively properties of the dot product. These also make reference to geometric features of Rn like magnitude and angle. Right? We don't have geometric notions like that in vector spaces. Right? What's the geometric magnitude of a solution to a differential equation? Right? What's the angle between two matrices? We don't have any sort of pre-existing notion. It wouldn't make any sense at all for me to require that inner product spaces have to have certain relationships in conjunction with ideas that don't exist. Right? So I can't make these part of the definition. They don't come along automatically. So what do we do with them? And the answer is actually quite nice. Because of exactly what we just talked about, I can take this formula here as the definition of a new concept. I can make that the definition of magnitude. New concept of magnitude in an inner product space. And likewise, I can take this formula here. I can make that the definition of a new notion of angle. Oh, come on, man. Angle. Definition of a new notion of angle in an inner product space. And this is a little weird, right? Let me remind you, we started off with vector spaces. The only constructions that we have in a vector space are you can add things, you can multiply by scalars, right? Think about, a vector space of a certain shape of matrices, for example. I think is a nice example. We had no previous notion of the magnitude of a matrix. Now we do. As long as we have an inner product, that inner product, by way of this formula, defines a notion of magnitude. Arguably even creepier. We have no idea, previous to this, what should it mean to talk about an angle between two matrices? There's no geometric, I don't know it's hard to make any sense out of that at all. But once you pick an inner product, we now have a definition of angle. So some examples. Where am I? Here's our definition of magnitude. Magnitude, motivated by how it worked with dot products, the magnitude of a vector in an inner product space is the square root of the self-inner product. Just like it was for dot products. So magnitude. Sometimes they call this a norm. Geometrically, you think of it as a length, just for sort of intuitive sense. Okay. Using the L2 inner product then, keep in mind we have a new inner product space, C, using our brand new L2 inner product, and with that inner product chosen, there's our notion of magnitude. Thought of as a vector in the inner product space, right? Thought of as a vector, the size, if you will, the length, the magnitude of that as a vector in the inner product space is this wacky little formula right here. Okay. Ditto with angle. Right? You give me, two vectors in an inner product space. We rip off the old formula from Rn. There's a notion of angle in Rn. This is the rip off of it in a general inner product space. And a nice example here. I'm going to skip the details of the calculation. It's just plug and chug. But if you take this vector, and if you take this vector, and you want to talk about, okay, inside of our new C0 inner product space, what is the angle between these two functions? There's a creepy thought, right? We're thinking, we've already had the idea of thinking of functions as being vectors, but now it's not just in a sort of an additive sense. We have a notion now of sort of relations, directional relationships, angles between two vectors in this inner product space. And the computation is just, it's straight out of this formula. That magnitude, straight by that definition, compute, it ends up being square root of pi. Quick aside, don't forget all your old Calc 2. Pratt has specifically asked us to make sure that students stay fresh with their Calc 2 skills. So make sure you can do this kind of a thing. This right here, right? That. Well, there's the definition of that magnitude. Compute. Make sure you can do that. Again, that's an old Calc 2 thing. You get that. And this dot product up here, inner product, that numerator is that. Make sure you can still do your calc too, and you get that formula right there. Okay. All right, how are we doing? Everybody on board? Okay, lots of algebraic details for y'all to fill in. I do want to sanity check this result. By the way, you plug all these numbers in that we just computed, and what we find is that the inner product space angle is equal to the phase shift, or the negative of the phase shift. And I want to sanity check that. First, let me point out why this is not obvious. This is very, very far from obvious. Here's the picture of what we're talking about here, the two functions. Our first function, let's see here, I'll use that first function, sine x, looks like this. My second function, oh gosh, I'll do this in orange. Second function is same thing, but kind of shifted over a little bit. Right, the phase shift is like that. There's your phase shift. The negative of the phase shift, excuse me. Okay, so let's kind of think through some scenarios. A quick observation, again, this angle and that angle are really, really different conceptually. This is a phase shift between two real valued periodic functions. It's just a phase shift. This is a trig concept from high school. This angle here is a brand new, very deep concept. This says, viewed as vectors in an inner product space, what is the angle in the inner product space that comes from the inner product? This is a high school concept. This is a deep concept. Right? So the fact that they're equal is a little bit weird, but I claim that's pretty plausible, actually. Let's think it through. A couple sanity checks. What does it look like if phi is 0? If phi is 0, these are the same function. Therefore, we're looking at two identical vectors. Two identical vectors, the angle between two identical vectors is 0. So when the phase shift is 0, the inner product space angle should be 0. Cool. What about if phi is small? Kind of like I have it drawn here. If phi is small, well, let's see here. Then notice that they're not the same functions. They're not the same vectors. But the value of the orange function, the value of the blue function, they're never that far off from each other. They kind of track each other. So they are not very far apart from each other in some sense as functions. And if two vectors are not very far apart from each other, then the angle should be small. So when the phase shift is small, the inner product space angle should be small. So again, sanity check. That's not a proof of anything. It's a plausibility argument. Lastly, what if phi is pi? Now let's think for a moment how phase shifts work and sine waves. When you phase shift by pi, the orange curve and the blue curve become exact negatives of each other. In an inner product space, vectors that are exact negatives of each other, the angle is pi. Right? So when the phase shift is pi, the inner product space angle also pi. So this doesn't prove anything, but this does kind of sanity check that this is somehow meaningful. It's kind of natural in ways that we might expect. Okay, let's see here. I have 1 minute left. Very quickly, I want to say that the Cauchy-Schwarz inequality that y'all remember from Math 212, something we kind of blow past in Math 212 pretty quickly, actually applies not just to the dot product as we stated it in Math 212. It applies to every inner product. That's why it's a big deal. That's why it has a name. That's why this is, the Cauchy-Schwarz inequality and that whole formula from Math 212 about, dot products involving cosine theta, and it doesn't have a name. That's a peculiarity of Math 212. This is a general truth about all inner products. This fact right here. So that's why it gets a name. Lastly, the very last example that I have in this section is a thing about statistics. It's a neat fact. It's not in the book. It's It's not essential to anything else that we're doing, and because we're behind schedule, I am not going to have time to talk about it. So we don't have to look at this example about statistics, but if you're curious, there's a really powerful point of view in here, and if you're interested in statistics, come by and talk to me. I'll explain. It's pretty neato. All right. Y'all have a great weekend. See you later.